In this lesson, we want to review systems of linear equations in two variables. And specifically, we're going to look at the graphing method, the substitution method, and the elimination method. So in this section of our course, we're going to do a deep dive into matrices. And before we can really get into this topic, we have to do a thorough review of the basics. So over the course of the next few lessons, we're going to revisit some stuff that you learned in Algebra 1 and Algebra 2, just to make sure you have a fundamental understanding of these kind of basic concepts before we get into this advanced material. So at this point, we've all seen a linear equation in two variables. We talked about this earlier in the course. Something like x plus y equals 1. Now, one thing I immediately want to kind of draw your attention to is that this type of equation has what? An infinite number of solutions. So there's an infinite number of x comma y values or ordered pairs that will satisfy this equation. We can find them by plugging in something for x and solving for y, or plugging something in for y and solving for x. Now the question you always get when you do this is, where did you get that number from? And the answer is I made it up, right? So I can choose any value I want for x. Anything I want. It could be 1,000,000 if I wanted it to. Okay, I'm not going to use that because it's a little big. I'm just going to use the number 2. Again, just made it up. Plug that in for x and then solve for y. So 2 plus y equals 1. So if I want to solve for y, I just subtract 2 away from each side of the equation. This cancels. I get y is equal to 1 minus 2 is negative 1. Okay, so what this tells me is that I plugged in a 2 for x. So when x is 2, y is negative 1. So that ordered pair, 2 comma negative 1, satisfies this equation. And I can do the same thing over and over and over again and generate an infinite number of these ordered pairs. I could choose something for y, like let's say 5. Again, where did I get 5 from? I made it up. So 5 gets plugged in for y. So you get x plus 5 equals 1. So if I subtract 5 away from each side of the equation, I get x is equal to negative 4. So now another ordered pair is negative 4 comma 5. Okay, again, we can continue doing this forever and ever and ever. Now, when we first look at linear equations in two variables, we do this kind of activity to generate enough ordered pairs so that we can kind of sketch our graph. But as we kind of move on, we find that there's an easier way to sketch our graph. And the way to do this is to solve the equation for y and put it in slope-intercept form. So looking at this guy, if I just solve it for y, if I subtract x away from each side, I get y is equal to negative x plus 1. Okay, so this is in the format of y equals m the slope times x plus b the y-intercept. So in this case, my slope m is negative 1, right? Because you should have a negative there. You could really erase that and put in negative 1 if you wanted to make that more clear. And b, my y-intercept is 1. So that means the y-intercept occurs at 0, right, for the x-coordinate, comma 1, this guy right here. So graphically, all I really need to do is find 0, comma 1, which is right here. That's my point. And then I can use my slope of negative 1 to generate additional points. Remember, slope m is rise over run. So if this is negative 1, and I could say it's over 1, right, because anything over 1 is just itself. Well, really, I could say, okay, from this point, I could fall 1, go to the right 1. Fall 1, go to the right 1. Fall 1, go to the right 1. You know, so on and so forth. I've given you this point here and this point here, but really you just need 2 points. So if I started there, I could go down 1 to the right 1 and have a point there. That's really enough to graph a line. But of course, I've already pre-drawn this, so we could have a nice clean line. I made it with a computer versus just freehand drawing, which generally doesn't look so good. All right, so we know that this is how we could graph this guy. And we also know that every point on this line is a solution for this equation. Let's just take this point right here, which is going to be 4 comma negative 3. So let's erase this real quick. I just want to show you this, just so you have a complete understanding. So that means if I plugged in a 4 for x and I plugged in a negative 3 for y, I should get a true statement. And obviously that would work because 4 plus negative 3 or 4 minus 3 would give me 1. Right? 4 minus 3 equals 1. You get 1 equals 1. So that's true. So again, every point on this line is a solution for this equation. Now, suppose we throw another equation into the mix and we consider these two equations together. So this is known as a system of linear equations. And in this case, because we have two variables involved, you could say it's a system of linear equations in two variables. Now, in this particular case, you're not going to have an infinite number of solutions because the solution now has to satisfy this equation and this equation. So that means whatever I get for x and whatever I get for y, I have to be able to plug in for x here and for y here and here, okay? And it has to satisfy both. So one way that we can find such a solution is using the kind of graphing method. It's not very efficient, okay, but it is a good way to teach the concept. So if we graph this one, x minus 2y equals negative 8, we would what? We could solve this for y, so x minus 2y equals negative 8. I would subtract x away from each side. So let me kind of do this up here. This would cancel. I'd have my negative 2y equals negative x minus 8. What I need to do now is get rid of this negative 2. So let me divide both sides by negative 2. And so this is going to cancel. And so now I'm going to have y is equal to, you essentially have negative over negative, which is positive. So this is x over 2, but we're going to just write this as what? Just 1/2 times x, and then negative 8 over negative 2 is plus 4. So you got y equals 1/2 x plus 4. So I'm going to add that. I'm going to say this is y equals 1/2 x plus 4. Okay, that's going to be this guy right here. Again, I would go to my y-intercept, which occurs at 0, 4. So that's going to be right here. And let me use a different color because that didn't show up so well. So let me use this color. And then I could find additional points with my slope. Again, m, my slope is 1/2. So it's rise over run. So it's 1 over 2. So I would rise 1, go to the right 1, 2. So there's a point. Or I could fall 1 and go to the left 1, 2. So there's a point. Now, let me draw your attention to this point right here. Okay, so this point lies on this line, y equals 1/2 x plus 4. And then also this line, which we already know, is y equals negative x plus 1, again, in slope-intercept form, or x plus y equals 1 in standard form. Either way you want to kind of label that. But the main thing to notice here is that that point that lies on both lines, or the intersection of these two, it's going to solve both equations because it's on both lines, right? Every point on the line is a solution for the equation. So every point on this yellow line is a solution for this equation. Every point on this, I guess you would say that's teal, every point on this teal line is a solution for this equation. That point of intersection, which is negative 2, 3, so let me label that. I'll label that over here. I'll say it's negative 2, 3. That guy is on both lines, so it solves both equations of the system, and so it's a solution for the system. If I go back, we can prove this mathematically, okay? And so let me just write the solution here as negative 2, 3. And you just plug in a negative 2 for each x and a 3 for each y, and you verify that it works in both equations, and then you know you have your correct solution. So in the first one, I would have negative 2 plus 3 equals 1. So we know that works, right? Because this is going to be 1 equals 1, so it works in this first one. Then for the second one, you would have negative 2 minus 2 times, plug in a 3 for y, and this equals negative 8. Okay, so I would start with negative 2 times 3, that's going to be negative 6. And then negative 2 minus 6 is negative 8. So you get negative 8 equals negative 8, so it works here as well. So we've found our solution for the system graphically. Again, all we really need to do there is graph each equation, okay, and then look for the point of intersection. Now, this method is not practical, okay? It's just something we use to teach the concept, because what if you have a solution like, 1/2, 2/19, something like that? That's not going to be very easy to find graphically. So fortunately for us, we have other methods, and these methods are algebraic, okay? So you already know that we have the substitution method and we have the elimination method. So let's start out with the substitution method. Let's use the exact same two equations. And for reference sake, I've labeled the top one as equation 1. That's why you see this 1 here. And I've labeled the bottom equation as equation 2, just so I can talk about it and say, okay, equation 1, I'm talking about this guy right here. If I say equation 2, I'm talking about this guy right here. Okay, just for reference. Now, with substitution, the idea is that we want to solve one of the equations for one of the variables, okay? Doesn't matter which one. And then you want to plug in for that variable and the other equation. What that's going to do is it's going to give you a linear equation in one variable, okay? So we can easily solve that, and then we're going to substitute back into one of the original equations and get the other one, okay? So what I just said might sound kind of complicated if you've never seen this before. If you have seen it, you know it's very easy. You usually want to use substitution when one of your variables has a coefficient of 1 or -1. In this case, with equation 1, you have a coefficient on x of 1, you have a coefficient on y of 1, and then also in equation 2, you have a coefficient on x of 1. Okay, so any of these would be easy to use. I'm just going to use equation 1, and I'm just going to solve it for y, because we already did that. So I'm just going to say that y is equal to what? I would subtract x away from each side, so it would be -x and then +1. Okay, so once you've done that, you've got it in terms of y. So now you're going to plug in for y in the other equation. So what do I mean by that? Here's y right here. We're saying y is equal to, or y is the same as, this -x + 1. So what I'm going to do here is I'm going to plug this guy right here in for y there. Okay, that's all I'm doing. It's very, very simple. So I have x minus 2. You've got to use parentheses here because 2 is multiplying this whole thing. So times the quantity. I'm going to use a different color for this. So -x + 1. And then I'll switch back. And then this is equal to -8. So let me scroll down and I'll come back up. You see that we only have one variable now. We only have x involved, okay? So we have x, and then I'm going to distribute this -2 to each term inside the parentheses. -2 times -x is going to be +2x. -2 times 1 is going to be -2. This equals -8. Okay, so combined like terms, x + 2x is 3x. And then I can add 2 to both sides of the equation. So -8 + 2 is going to be -6. Lastly, I want x by itself, so I'm just going to divide both sides by 3, and I find that x is equal to -2. We already knew that because we solved this already using graphing, but we just solved it using substitution, and we found that x is -2. So let me erase this, and we can erase this as well. So I'm just going to put this over here and say that x is equal to -2. Okay, now we already know because we solved this already that y is +3, but let's prove this. What we would do, once we found one of the variables, we can plug into either original equation, and we can find the other. So I can just plug in here, or I can plug in here. Doesn't matter. So let's just plug a -2 in for x in equation 2. So -2 minus 2y equals -8. And let me add 2 to both sides of the equation. That will cancel. We'll have -2y is equal to -8 plus 2 is going to be -6. And let me scroll down a little bit, get a little room. And let me divide both sides by -2 so I can isolate y. So this cancels. We found that, again, y equals +3. Let me erase this, and let's go back up. So y is equal to 3. Okay, so -2 comma 3 as an ordered pair. And we've already checked this, so we don't need to check it again. But again, that's the substitution method. So let's look at a harder example of this. So now we have -9x minus 10y equals 5, and -7x minus 6y equals 11. So let me label this as equation 1, and this is equation 2. Again, just for reference sake. So what I'm going to do is I'm going to solve one of these for one of the variables, and then I'm going to plug in for that variable in the other equation. So I can solve for x, I can solve for y. Here it really doesn't make a difference. You don't have anything that's easier. I'm just going to work with equation 1, and I'm going to solve it for x. Okay, so I'm going to solve for x. So I have -9x minus 10y equals 5. To solve for x, I want to isolate x on one side. Okay, so that's all I want to do. So I'm going to start by isolating this term. So add 10y to both sides. Let me scroll down and get some room going. So this will cancel, obviously. We'll have -9x is equal to, you'll have 10y plus 5. Okay, so how can I get x by itself? Well, what I want to do is get rid of this -9 that's multiplying x. So I'm going to divide both sides by -9. And of course, this is going to cancel. Let me kind of drag this up here. We'll have x is equal to, you have 10 over -9. We'll just say -10/9. And then times y. And then you'll have -5/9. Okay? So a lot messier than what we saw in the last example. But this is a typical thing that you'll see as you get into kind of more challenging examples. So let me erase this. And now we've solved this guy for x, okay? So we've solved it for x. Let me scroll up and let me drag this up. So we used equation 1. So now what I want to do is use equation 2. And again, I want to plug in for x there. I have x now. It's equal to this or it's the same as this. So I'm going to take this and I'm going to plug it in for x there. So I'm going to have negative 7 times, again, the quantity. You need parentheses because negative 7 is multiplying this whole thing. So let me do this in a different color. So you have negative 10 ninths times y, and then minus 5 ninths. And let me go back to this color. And then we'll have our minus 6y, and then we'll have that it equals 11. So notice that I only have a y involved, right? There's no x. So that's why this method works, right? It breaks it down into kind of a linear equation in one variable that you can solve, then you can go back and substitute and get the other value that you're looking for. So now let me kind of distribute this negative 7 to each term. This would be positive 70 ninths times y. Then this would be positive 35 ninths. And then we'd have minus 6y, and this equals 11. Now to make this a little bit quicker, if you don't want to work with fractions, remember we can just multiply both sides of the equation by this LCD, 9. So I would have what? I would have 70y plus 35. Then minus, if I multiplied 9 times 6, it would be 54. Then times that y, and this equals 9 times 11 is 99. So from this point, I can combine like terms here. 70y minus 54y would be 16y. And then let me say plus 35 equals 99. I'm going to subtract 35 away from each side of the equation. This will cancel. We'll have our 16y is equal to, if I do 99 minus 35, that's going to give me 64. If I then divide both sides by 16, I'll find that y is equal to 4. Okay, so let's erase all this. All right, so at this point, we know that y equals 4. And again, let me put these numbers back up so I can refer to these equations. And now I can just plug a 4 in for y in either equation 1 or 2. Doesn't matter. Let's just use 2. So we'd have negative 7x minus 6 times, again, plug in a 4 for y, equals 11. So now I can solve for x. So negative 6 times 4 would be negative 24. And what I can do now is just add 24 to both sides of the equation. So this is going to go away over here. 11 plus 24 is 35. So this would be equals 35. And then what I can do to finish this off is just divide both sides by negative 7. And I'll find that x is equal to negative 5. Okay, so x is equal to negative 5. Again, as an ordered pair, we could say this is negative 5, 4. And if you want to check this, plug a negative 5 in for each x, plug a 4 in for each y, verify you got the right answer. So negative 9 times negative 5 minus 10 times 4 equals 5. Is that true? Negative 9 times negative 5 is 45. Negative 10 times 4 is 40, so minus 40. And this equals 5. This is true. 45 minus 40 is 5. That one works out. Then the other one would be what? It would be negative 7 times, you have negative 5, minus 6 times, you have 4. This equals 11. Negative 7 times negative 5 is 35. Minus 6 times 4. 6 times 4 is 24. We know that 35 minus 24 is 11, so that one checks out as well. So negative 5, 4 is the solution for this system. All right, so now let's move on and talk about the elimination method. The elimination method is probably a little bit more preferred, but if you have a situation like we just looked at, it really can go either way, okay? But the elimination method does require a little bit of extra work. So the first thing you have to do is you have to make sure that the equations are written in standard form. So that's the ax plus by equals c. Now, when we did our lesson on this, we talked about there being kind of a high school definition and then being kind of a relaxed definition as you move on. A, B, and C here can be any real number that you want. They don't have to be, positive for A, and it doesn't have to be an integer. Any real number will do for A, B, and C. Just write it in this format. So what we would do here is we would subtract 7y away from each side of the equation. So that would give me, I would say this is equation 1. I would have 6x minus 7y. This would be equal to 9, right? So this is ax plus by equals c, okay? And then over here, for equation 2, we'll say, I would add 2x to both sides. So I would have 2x plus y is equal to negative 7. Okay, so this is the format that we wanted in. Now, the idea here is that once you have each equation written in standard form, you want to think about how you can make the coefficients of one pair of variable terms into opposites. So this is really easy to do. In this particular case, you'll notice that this guy right here is a negative 7, the coefficient of y. And this guy, if I kind of erase this and make this plus 1, this guy is a 1, okay? So this guy is a negative 7, and this guy is a 1. So we know we can multiply both sides of an equation by the same non-zero number and not change the solution. So what I could do is I could multiply equation 2 by 7. So if I did that, 2x times 7 is 14x. 1y times 7 is going to be plus 7y. And then negative 7 times 7 is negative 49. So notice how, if we kind of look at it this way, this guy right here, this negative 7, and this guy right here, positive 7, those guys are opposites, okay? And we need that because one of the variables is going to drop out in the next step when we achieve this. So what I'm going to do now is I'm just going to take this 6x minus 7y equals 9, and I'm going to add the two left sides, and I'm going to set this equal to the sum of the two right sides. So let's do this real quick, and then I'll explain why this works mathematically. So 14x plus 6x is going to give me 20x. And then 7y minus 7y, those are going to go away, right? That's going to be eliminated. So this would be equal to, if we have negative 49 plus 9, this is going to be negative 40. So at this point, we see that we only have one variable involved. So we can just divide both sides by 20 and find that x is equal to negative 2. Okay, so very, very simple. So let me erase this. We don't even need this anymore. I'm just going to write that x equals negative 2. And let me explain why this worked, and then we'll find why. Okay. So why was I able to add this to this and set this equal to this plus this? Well, let's just think back to the addition property of equality for a moment. We know that if I have A equals C, and this is very generic, if I had A plus B, this is equal to C plus B. So in other words, if these two quantities started off as being equal, and I add the same number to both sides, it's still equal, okay? So in other words, if I had x plus 4 equals 7, we know at this point that I could add something like 3 to both sides of the equation. So x plus 4 plus 3 equals 7 plus 3, and I've got the same solution. Here the solution is 3, right? 3 plus 4 is 7. Here the solution is still 3. 3 plus 4 is 7. 7 plus 3 is 10. Over here I have 7 plus 3, which is also 10. So adding the same number to both sides did not change the solution. Now, it's the same thing here, okay? It's just a little bit more complicated to understand. Remember that this guy is set equal to this guy. So they're the same, okay? They're set equal to each other. So what I'm doing is I'm adding this to this side, and I'm adding this to this side. So I'm adding the same thing or the same quantity to both sides of the equation. It just looks different, okay? It just looks different. So that's what you need to understand about this method. Now, let's erase this. And let's find y. So I can just plug in a negative 2 here, or I can plug it in there, it doesn't matter. Okay, and you can find y that way. So y equals negative 2 times negative 2 minus 7. Negative 2 times negative 2 is 4. And then 4 minus 7 is going to give you negative 3. So y here is negative 3. So as an ordered pair, this is negative 2, comma, and then you have negative 3. Okay, so let's check this real quick. So 6 times negative 2 equals 7 times negative 3 plus 9. 7 times negative 3 is negative 21. Negative 21 plus 9 is negative 12. And obviously 6 times negative 2 is negative 12, so this works out. Then for this one, y, which is negative 3, is equal to negative 2 times negative 2 minus 7. We already know this is true because we just did it. This is 4 minus 7, which is negative 3, so this works out as well. All right, let's do one more of these, and then we'll kind of move on to some systems that don't have a solution or an infinite number of solutions. All right, so we have negative 7x equals negative 6y minus 10. We have 4y equals 5x minus 8. Again, the first step when you want to use elimination, you've got to put everything in standard form. So I would just say that this guy right here is negative 7x. And let me label this as equation 1 so we can keep track. So again, it's negative 7x. I would add 6y to both sides, so plus 6y. And this is equal to negative 10. Okay. Then for my equation 2, I would have what? I would subtract 5x away from each side. So I would have negative 5x plus 4y is equal to negative 8. Okay. All right. So now that we have this set up, we want to think about how we can eliminate a variable. So to do this, what I'm going to do is I'm going to look at y. And notice how this is a 6 and this is a 4. Well, the least common multiple of 4 and 6 is going to be 12. So what I can do here is I can multiply equation 1 by negative 2, right? Because 6 times negative 2 would be negative 12. So negative 7 times negative 2 would be 14, then times x. Then 6 times negative 2 would be negative 12, then times y. And this equals negative 10 times negative 2 is 20. Okay? When you do this, make sure you multiply every part of that equation by that number, okay, to make it legal. Then for this guy right here, again, my least common multiple between 6 and 4 we said was 12. I made this one negative 12, so this one's going to be positive 12. So I'm going to multiply this by 3, right, this equation. So negative 5 times 3 is going to be negative 15, then times x. And then 4 times 3 is 12, so plus 12, and then times y. And this equals negative 8 times 3 is negative 24. Now, we have opposite coefficients on our variable y. We have negative 12 and positive 12, okay? So let's scooch this down here. And again, what we want to do is add the two left sides and set that equal to the sum of the right sides. So 14x minus 15x is going to be negative x. This is going to cancel, right? Negative 12y plus 12y, that's gone. And this equals 20 minus 24, which is negative 4. Divide both sides by negative 1, and you get that x is equal to 4. Okay, so that was pretty quick. So x is equal to 4, and pretty easy method overall. So x equals 4. Plug this in for x in one of the original equations. So let's plug that in there, see what we get. 4y is equal to 5 times 4, which is 20, minus 8. 20 minus 8 is 12, right? And we can all see that y is 3, right? Divide both sides by 4. You get that y is equal to 3. So we'll put our solution as 4, 3. So let's check this real quick. So if I plug in a 4 here in the top equation for x, negative 7 times 4 is equal to negative 6 times, plug in a 3 for y, then minus 10. Negative 7 times 4 is negative 28. This equals negative 6 times 3, which is negative 18, minus 10. Obviously, negative 18 minus 10 is negative 28, so this one works out. Then for the other one, 4 times 3 is 12. And this equals 5 times 4, which is 20, minus 8, which is 12. So this one works out as well. All right, so at this point, we've only looked at systems that have graphs that intersect at a single point. When we see this type of situation, you're going to have a system that's known as being consistent, and the equations are said to be independent, okay? But most of you already know that there's some special case scenarios that you're going to encounter. You're going to come across a linear system with no solution. This is referred to as an inconsistent system. This happens when the two lines are parallel. And then we're also going to have another situation where we have an infinite number of solutions. In that case, the equations are said to be dependent. But let's start out by looking at an example where there's no solution. Let's just go through this and use the substitution method and see what we end up with. So we have 2y equals 10x plus 6 and negative 5x plus y equals negative 7. The reason I'm choosing substitution here is because this coefficient is a 1. So it's really easy to solve this for y. I can just add 5x to both sides. And my second equation here, my bottom equation, is going to be y is equal to 5x minus 7. Okay, so let's erase this. And all I need to do now is just plug in for y in this first equation, this top equation. So this guy right here, if I highlight that and I highlight this, again, this right here, this is what y is equal to or the same as. I'm just going to plug that in there, and I'll have a linear equation in one variable. Okay, a linear equation with just x involved. So I would have 2 times, again, use parentheses. So we're going to have 5x minus 7. And this is equal to, you're going to have your 10x plus 6. Okay, so let's just go ahead and solve this. 2 times 5x is 10x. 2 times negative 7 is negative 14. This equals, you have 10x plus 6. And so over here, you notice that I have 10x and 10x on each side of the equation. So immediately you see you have some kind of problem. Okay, you might not know what it is, but let's say I subtracted 10x away from each side. Right? If I have the same thing on each side, I can just get rid of it. So if I erase this from each side, what do I get? I get nonsense, right? I get negative 14 equals 6, which is never true, right? This is a false statement. So when you solve this type of system with either substitution or elimination, you're going to end up with a false statement. So that's how you know you can stop and say there's no solution. Essentially, you want to write the symbol for the null or empty set, meaning the solution set contains no elements. Now, You can also see this graphically. If I solved each one of these for y, you would notice that the slopes are the same, right? Because parallel lines have the same slope in different y-intercepts. Parallel lines are never going to intersect, right? So that's the definition of them. So if I solve this for y again, we know that it's y equals 5x minus 7. This guy, if I solve it for y, I have what? I have 2y equals 10x plus 6. I just divide everything by 2, right? So I can get y by itself. And I'm going to have that y is equal to 10 over 2 is 5 times x, and then plus 6 divided by 2 is 3. So if you see this and you notice that you have the same slope in different y-intercepts, you already know not to even work this problem. Just stop and say there's no solution because you have two parallel lines. If we copy this, kind of come here, I've already graphed this to show you what this looks like. So we have y equals 5x plus 3. That's going to be this guy in orange, right? This is my y equals 5x plus 3. Let me erase it from here. And my guy in teal, again, I don't know what color that is. I think it's teal. The guy in teal is going to be this y equals 5x minus 7, okay? So you can see for this guy, y equals 5x plus 3, you have a y-intercept that occurs at 0, 3, and a slope of positive 5. So up 1, 2, 3, 4, 5, to the right 1. For this guy, y equals 5x minus 7, the y-intercept occurs at 0, negative 7, so right there. And again, the slope is 5. So up 1, 2, 3, 4, 5, to the right 1. Okay, so those are the two lines. You can see they have the same slope. So they continue like this forever in each direction. They're never going to intersect. Okay, they're always going to be apart from each other. There's no point that lies on both lines, so there's never going to be a solution for that system. So to show this with elimination, let's just start by making this equation 1. We'll label it. And again, I want these in standard form. This guy's going to be equation 2. So for the one in equation 2, it's already ready to go. It's negative 5x plus y equals negative 7. Again, we're using a looser definition, so this guy can be negative. It's ax plus by equals c. Again, where a, b, and c, those are just real numbers at this point, okay? And then for equation 1, I'm just going to subtract 10x away from each side. So that would give me negative 10x and then plus 2y. And this equals 6. So if you want to, you can divide both sides of equation 1 by something like 2 to make it simpler. So this would be negative 5. This would just be y, and this would be 3, okay? So now what we're going to see is we're going to have a problem, right? If we go through the elimination method, we want to set it up to where kind of one pair of variable terms has opposite coefficients, okay? If I take, let's say, equation 1, and I say, well, if I multiply this by negative 1, I would have positive 5x and negative 5x, but also I'd have negative y and positive y. So that's going to be a problem because both those variables are going to drop out, right? So you're going to end up with 0 equals something. And 0 equals something other than 0, okay, is going to be a false statement. So let's just go ahead and do that. Let's multiply equation 1 by negative 1. So I would have positive 5x minus y equals negative 3. And then this guy right here, this negative 5x plus y equals negative 7. So we add the two left sides and they cancel. So you get 0. This is equal to negative 3 plus negative 7, which is negative 10, which is always false. Okay. So again, if you solve something like this and you get a false statement, you can say there's no solution, right? You basically have parallel lines. They're never going to intersect. So it's not possible to have a solution. All right. So let's wrap up our lesson and look at the other special case scenario. So for this scenario, you're basically going to be given the same equation twice, right? It's going to be algebraically manipulated to look different, but it's the same equation. Okay, so when you get this situation, you're going to say the equations are dependent, and you're going to have an infinite number of solutions because whatever works in kind of the top equation is also going to work in the bottom equation because they're the same equation, okay? You could see that if you look at this top equation and this bottom equation here, for negative 3x minus 15y equals 45, and x plus 5y equals negative 15, well, if I divided the top equation by negative 3, so negative 3x divided by negative 3 would be x. Negative 15y divided by negative 3 would be plus 5y. This equals 45 divided by negative 3 is negative 15. So you have the same equation here and here. Okay, so it's just algebraically manipulated to look different, but essentially you have an infinite number of solutions for this type of scenario. Now, if we solve this guy using substitution and we don't realize this, or we solve it using elimination and we don't realize this, you're just going to end up with a true statement. Okay. Okay, we saw when we solved an inconsistent system or a system with no solution that you ended up with a false statement. Now you're going to end up with a true statement. Okay, so that's how you know the difference between the two. So let's solve this with substitution real quick. So I know that this is going to be easy to solve for substitution because the coefficient on that x is a 1. So I can solve this for x and say x is equal to negative 5y minus 15. So then I can plug in for x here, and I can plug this in, right? So this is going to go right there. So let's go ahead and do that real quick. I'm going to have negative 3 times, again, I'm plugging this in for x. So negative 5y minus 15, and then minus 15y, and this equals 45. Let me scroll down and get a little room going. And let's just go ahead and distribute. So negative 3 times negative 5y would be 15y. Negative 3 times negative 15 is going to be plus 45. And then you have minus 15y, and this equals 45. So you can see you have a problem, right? Because you have this will cancel with this. So you just have 45 equals 45, which is always true, okay? And you can subtract 45 away from each side and say you have 0 equals 0, but it doesn't matter. You still have something that's true, okay? So when this scenario occurs, whether you're doing substitution or elimination, I'll let you do that on your own if you want to try it that way, you just end up with a true statement. So that's how you know you have an infinite number of solutions. And I'll just write this out real quick, and I'll say there's an infinite number of solutions. Okay, so that would be our answer for this type of problem.